Hi, welcome to the Signal Path. In this episode, we're going to do another product review and check out what I have here. This is the Rohde Schwarz LCX200, the new platform of LCR meters that Rohde Schwarz has introduced a short while ago based on their new GUI and operating system with LCD interface, similar to, for example, the power supply you see here at the bottom. Now, there's a lot to talk about here. This is a 0.05% impedance measurement unit, 0.03 degrees. It can go all the way to 10 megahertz with the appropriate options, external bias, a whole bunch of functionality on binning and tracing and logging. So there's a lot to talk about. I also want to do a teardown, of course. Now I want this to also be a bit of a tutorial on measurement techniques as well as how to use this instrument. Let's get started. And here's the Rohde Schwarz LCX200 LCR meter. It's built on the same modern platform that Rohde Schwarz has been using for a lot of instruments in the same form factor. It has the same operating system, same touchscreen LCD, as well as the menu manipulation. Soon you'll find yourself pressing the similar buttons among very different instruments to get to where you want. And they've really kept that philosophy of the OS language the same, which I really like. It makes it quite easy to use. We do have a soft power button in the front with a shroud so you don't accidentally press it, USB and a few other things to manipulate the core operating system, the settings and menus. Here we have all the buttons that lay out the LCR functions. Most of them light up, and I find that they have made the right choices. I use these buttons all the time, even though the LCD screen is also available. I think it's a good compromise. There is no touch button for the numbers. You have to use the LCD screen for that, which works reasonably well. It is quite reflective, as it always is with these instruments, but the screen is really bright, so I haven't found much issue with it. Here's the ground in the front if you need that, and then there is our 4 ports for making the LCR measurements. The rotation knob is also selectable. Overall, I find it really easy to manipulate through, as we will see once we are actually playing with the instrument. And here's the back of the instrument. We do have a LAN port USB device and an extra USB host, which is great. And here's the interface slot. It's just not populated in this particular unit. And our trigger input, which is tied to the software, some automated measurements and external triggering. And here's the external bias input port. We do have a dedicated fuse, which is fantastic, and this does go to 40 volts, which is great, quite a bit higher than some of the other competitive units, but it does not allow the reverse biasing, which means you always have to apply the positive and negative, and if you want to switch it, you'll have to physically flip the polarity. I wish this was in the front. It'd be a little bit more convenient, but it works in the back too. And here's the digital I/O, which is also tied into things like binning and triggering and so on, which can be programmed and configured, a lock, and of course the AC line with a dedicated switch, which is also great. One additional comment about the external voltage bias. When we do a teardown, you'll see the components used to handle this plus 40 volt in. In order for this to be plus and minus 40 volt, you'd have to double that entire circuitry, essentially build a quasi SMU front end. It's a matter of economy and the cost profile of the instrument, but hopefully in some of the future more advanced versions, you will be able to have both. So we have our LCR meter, but how do we connect our device under test to it? As to be expected, Rohde Schwarz has a wide range of test fixtures that we can use depending on what is optimum for the device we're measuring. I have a subset of them, some examples here. This is a Kelvin clip tweezer that we can use for measuring surface mount components. There's also regular Kelvin clips that is currently connected to the LCR meter. This is a transformer interface, making transformer measurements quite a bit easier, and these are for through-hole devices that directly you can plug into this. And this is for surface mount components as well, very precise spacing, and we'll take a look at that, and we'll use all of these during the experiments today. And this is a low inductance shunt that you can plug in directly to this to help calibrate the instrument. We will see that too. Now, interestingly enough, for Rohde Schwarz, they have a slightly different approach where there are 4 of these clips that allow you to basically secure this into the unit easily, but some of the other similar ones only have 2. Now, I find that this is a little bit more difficult to plug in, but I feel it makes a better connection than the ones where the 2 middle ones essentially don't have the outer connector of the BNC. Either way, both of them work just well. So here on the left side, I have the Rohde Schwarz test fixture for measuring surface mount components, and I have a different brand here on the right. Let's see how they are constructed internally. There are some subtle differences. So here on the Rohde Schwarz on the left, you can see that all the 4 ports are brought in as close to the DUT as possible before they join. Here they've decided to join them earlier on, and only a single wire goes to the actual test heads. I think I prefer the one on the left a little bit more, just simply because it brings that Kelvin connection really close in there. But internally, they're essentially doing the same thing. And here's what's inside of this Rohde Schwarz LCR meter, and look how beautifully it is put together, as to be expected from good Rohde Schwarz engineering. Now at the very bottom we have the AC line. Power comes in, goes into a power supply tucked away as far away as possible from the rest of the instrument in its own cage. Now this is a single voltage power supply, only generates 24 volts. Now a mixed signal instrument like this requires many other power supplies, and they have moved that all off into this board. The advantage of using a single power supply here is that you can engineer your power supplies the way you want them to be and shape their noise characteristics to work within the application. And the complication is that, well, you have to design all of that yourself, which of course is not a problem for an instrument of this caliber. As a result, the 24 volt coming over here goes everything under this cage, and these are where all the DC-DC converters are, generating many different power supplies, which are then routed and sent to the main LCR board. As a result, you completely isolate everything from this side to the right side. Not only that, they also have put all the DC-DC converters under a cage. That's how much they care about the noise inside of this unit, because you're dealing with extremely small current and voltage measurements in order to make the LCR work, especially with the very low voltage incidence that this thing supports. Now, at the same time, this board includes a few other things. For example, it accepts the external voltage to be applied to bias whatever you're connected. That's a nice touch. It goes over there and eventually reaches the front of the instrument. And then we have some protection circuitry over here, and we do have the USB, Ethernet, and everything else in the back. But this is actually not where the computer is. The computer is in the front of the instrument, much like many units we've seen in the recent years. Because of the miniaturization of these application processors, essentially they run an operating system in the lid, in the front panel of the unit, and the rest of it is just going to be changed depending on the application. So you can use the same front to build a power supply or an LCR meter, as we have seen Rohde Schwarz do in their modern instruments. The entire LCR functionality is maintained over here. There's an Altera Cyclone FPGA here, which is the glue that connects everything together. Also has interface to the back of the unit, and also the interface to the front display, which talks back to it. So it's all connected really nicely, isolated based on function. Ethernet cable runs here to the back, and that's what routes all of the interfaces to the back. It's not really used for anything else. Now, there's a lot going on underneath these cages, but let's go ahead and take a quick look at some of these circuitries over here and get some further insight. A quick look at the interface for the external voltage that can be applied from the outside. We do have a common mode inductor over here. This is a common mode choke to filter everything else. We do have an additional fuse, which is nice because we do have a user replaceable fuse, but there's also an internal one for more protection. All the IOs are also well protected. And we do have one of these PCB mounted heatsinks. The IC underneath is not connected to the heatsink directly. It is soldered to the PCB, and then you have these vertical lines coming out and then further spreading out to allow the heat to come out from multiple directions. This has become more and more popular because the PCB technologies allow you to put so much metal with so many layers that you have a good lateral dissipation. So you go laterally up and then through the fins. This is now quite common. And here is the front panel computer. Tucked away near the front panel LCD, we have the application processor, memories, flash, and other kinds. We have the ribbon cable controlling the LCR meter, and the ribbon cable connected to the front panel LCD screen. Accompanying DC-DC converters and power supply regulation, we also have the backup battery over here and a tiny little board which connects to the front panel USB. Because everything is so compact, the USB port extends too far into the instrument and has to go beyond the surface of this computer, and they need this little wraparound board to bring into the front. It's funny that they want to save this space so much that it's worth the additional engineering of that little piece. And over here on the left side, we can see the Ethernet port and the accompanying magnetics. We do have a power supply connector right over there. That's this white connector, and that comes from a separate place also, because this is all a digital circuit. You don't want that to interact with a sensitive power supply of the LCR meter, and these are all been engineered separately from each other. And if you look over here, you notice something interesting. These are the 4 BNCs that connect to the front of the panel of the unit. There are no cables. In most other LCR meters that we have taken apart, there's always a coaxial cable that comes from these 4 connectors and then wraps around and goes into the board, sometimes with ferrite cores around them to minimize their inductance and interaction. Here they've said, no, we're going to bring this as close to the board as possible. We don't want any cable. We want to get as much performance as possible. This makes the design of this whole thing a lot harder, because now you have to co-design everything mechanically together to make sure it fits together. But it's a good price to pay if you want to bring those, get rid of any of those parasitics from the system. And I'm sure you want to see what's underneath those cages, so I've gone ahead and removed them. I had to remove the entire board from the instrument because the cages are clipped from the other side. And look how beautiful the layout of everything is. Individual cages which separate the H and L ports of the instrument. Now this is based on an auto-balancing bridge. I've talked about that in one of the previous videos, so I won't dive too much into the details of it here. Definitely check that out if you want to understand how an LCR meter like this actually can do this kind of measurement. Now we do find most of the components we would expect. We do have our DAC over here, it's generating our source. This is a fairly high performance DAC, 14-bit over 200 megasample per second, and there's also on the other side of the board, which are routed to the front. And we do have filters that follow it. Now, building an LCR meter like this using DACs can go to very high frequencies, but everything gets harder in building an auto balancing bridge at higher frequencies. All your switches and op amps and feedback networks now to run at much higher frequencies and be stable and be very flat in frequency response. That's not easy to do in mixed signal circuitry like this. And we do have this section over here, which is an auto ranging circuit. We have high precision resistors and switches that switch around, allowing you to measure very small currents to very large currents, which is necessary for the high dynamic range in measurement of this instrument for both capacitance and inductance. Here on the left side, we have something interesting, a 2500 volt per microsecond slew rate buffer. It's a driver that goes up to 40 volts and is specifically designed to drive high capacitance and high inductance loads. And clearly this can be used to provide biasing to our circuitry, and that's why it is placed over here. Nice to see that that's how they've separated everything, and that's how they accomplished a very high DC bias internally capable of this unit. We saw the Altera FPGA here on the right side, completely isolated from everything else as well. There's another DAC on the other side of the board as well, and a whole bunch of modulators and demodulators which work in conjunction with the incident frequencies to make everything work. A whole bunch of protection circuitry. We have common mode chokes here in the front, as you can see. If I go up a little bit higher, the connectors are directly mounted to the board, minimizing all the interface inductances and capacitances and all the interactions they may have with each other. And these are our genuine Panasonic switches. They're pretty important to be of high quality because they switch a lot depending on how the auto ranging is set inside the instrument and how many different values of measurements are being done in a row. So it's good to see that high quality components are used throughout the unit. So let's go ahead and use the instrument. And in order to make the recording easier, so I don't have to record a display of the unit, I have a webcam over here where we can see live what I'm doing, but I've also logged into the instrument remotely using an Ethernet interface with the built-in VNC of the unit. Now, Rohde Schwarz has some of the best remote interfaces in the industry, and this is just running natively in a browser that I have full screen, which is fantastic, makes it a lot easier to use the unit. Now let's look at the display and what's on there, because there's a lot of information and it's been chosen very carefully. Now, first thing to note is that we are measuring CSRS and CPRP at the same time. I haven't seen a lot of LCR units that show you the parallel and series combination simultaneously. This can be really helpful, especially if you're not sure which equivalent model is best. And that depends a lot on the equivalent impedance at the particular frequency you're using and the characteristic of the passive that you're using. And this can be really helpful to find out if you're on the right track. Now at the bottom, the instrument measures the actual incident voltage and the measured current that's being applied to the device under test, but it also shows you two other parameters, which is the confidence in the measurement of the impedance and the phase. This too is extremely helpful, especially if you are near the borders of the accuracy of the instrument. It tells you right away whether you're in a favorable spot or not, or how much confidence you can have in your measurement, and this is a complex calculation that is done internally. Now if I click on this, I will immediately get the option of choosing quality factors or dissipation factor of the particular device we're measuring. This is capacitance, of course, but if you click over here, we get also a whole bunch of additional measurements. Now here we can plot things like impedance and phase in degrees and radius, as well as a whole bunch of other parameters. It's really nice to be able to have two of these on the screen at the same time. I find it really, really helpful. Now right now, as you can see here at the bottom, there's nothing connected to those Kelvin clips, so we're basically measuring this open capacitance. And the reason we're seeing it is because I have not calibrated the unit to get rid of it. So here now I have moved the probes on top of each other so that they're roughly at the same distance they would be when I want to measure my device. Now the coupling capacitance between them right now is 1.3 picofarad, and we want to get rid of this. Before we do this, let's make sure the settings are where we want them to be. The frequency is set to 1 kilohertz. Now in this instrument, you can set the frequency from 4 Hz all the way to 10 megahertz, which is a fairly broad range. It means that you can measure all kind of different passives across a variety of self-resonance frequencies. And the frequencies are not quantized. You can set them to anything you want. So for example, I can set it to 123 Hz, and you should have no problem with that. And this is because we saw internally the architecture was using these DACs and modulators and demodulators, allowing you complete freedom to set the frequency like you would in a synthesizer. So let's go ahead and put this back to 1 kilohertz where we want it. Now the voltage level applied here is 1 volt RMS. I'm going to set the range to auto. I'll talk about the auto ranging a little bit later on. But let's get rid of this coupling capacitor here. So if you go under compensation, under compensation you have open and short correction as well as load correction, which is very typical for LCR meters. Now under open correction we have two additional options. We can do it on the spot, meaning that the setting that the instrument currently has is what the open calibration will be applied to. Or you can do a full calibration where the instrument would sweep across its internal frequencies and settings to make sure that if you ever change something, you still have those calibration in the memory. The full one obviously takes a lot longer. So let's go ahead and do one right here. This is not going to take very long. It's going to take about maybe 10 seconds or so. And this is going to essentially get rid of these coupling capacitance that we had. There you go. This is already done. Now if I go back, you can see that that essentially is gone. So we are at the noise floor of the instrument at this point. Now remember that this open correction is really only meaningful if the capacitances you're trying to measure are comparable to these parasitic capacitance initially. The capacitors I want to measure next is not, but nonetheless it's important to know how to do this. You can similarly do the same thing for the short correction as well, which will give you much better resistance accurate measurements. So let's first measure something that we really understand. This is a capacitor standard box. It's a 1 microfarad, 0.05% tolerance. So it's very accurate and it's been calibrated already, so I know the value exactly. Let's go ahead and plug it in, and we should see a result very, very close to where we got. Look at that, 1.0005 microfarad. Now let's play with the settings of the instrument and see how it affects the measurement. First of all, I changed this to impedance and phase. If you look at the phase, minus 89.99, essentially minus 90 degree, means that we are very far away from the self-resonance of this capacitor, and we can rely on this capacitor's measurement and the equivalent model here. And in fact, this capacitor is rated for over 10 kilohertz, and that makes sense because we're only at 1 kilohertz here. Now, the other thing to look at is the actual measured voltage and current inside of the instrument. We're measuring 847 millivolt and about 5 milliamp, which puts us in a nice sweet spot in the measurement range of the unit. As a result, the confidence reported by the instrument on this measurement is pretty good, 0.081% for the impedance. So we can rely on this measurement. But this is at a very high input voltage level, 1 volt RMS. If I step it down, I'm going to push the signal measurements to be smaller and smaller, and eventually I'm going to hurt the confidence in the measurement, and the unit should tell us that. Let's go ahead and try it out. So I'm going to step it down by about 100 millivolts at a time. Let's go all the way to, let's say, half of that. Look at that. We've gotten a little bit worse. No change really observed here yet, but we can see that we're getting worse and worse. Let's go to 100 millivolt. Here's 100 millivolt. We're getting worse yet. A minor shift in the capacitance, and we can go all the way down to 10 millivolt RMS, and now we're beginning to drift a little bit away from where we were, and the confidence has gotten quite a bit worse as a result of that. But that's because we're now measuring 53 microamp RMS inside of the unit, and that is to be expected. Now, being able to apply 10 millivolt RMS to a device while you're measuring this capacitance and phase and so on is pretty helpful. Imagine if this was in circuit, surrounded by a whole bunch of active circuitry, and you wouldn't want to interfere with that and measure just the device while it is in circuit. This would be a really good way to do that. You can also, of course, go the other way, increase the voltage further. Let's go and try that and see what happens in that situation. So here's at 2 volt. You can see nothing much changes yet. Here's 3. Now once I'm at 3, we're now drawing so much current that the range of 100 ohm can no longer be used to measure RS. In fact, 100 ohm is the smallest range I have in this case anyway, so even if I remove the auto ranging, I still won't be able to measure it. These ranges are not available in this condition. I'll show you why in just a second. So it means that with a 3 volt RMS, I can still get my impedance measurements, and the measurements of the voltage and the current are there, but unfortunately I can no longer get the RS measurement as a result of that. And we can go further than this, of course. We can go higher and higher. We can go all the way to 10 volt RMS, like so. There you go, 10 volt RMS. Our measurement increases, and this is normal. This capacitance does indeed go up a little bit at higher incident voltages, as a lot of capacitors do experience some drift as a result of that. But yeah, unfortunately, we can no longer make the measurement. Now, this instrument does have one other capability. Let me actually keep this at 10 volt RMS here, and that is to change the source impedance internally. If I go over here in the measurement setup, I can go down here and I can change the source impedance to be 10 ohm. Now for capacitances or for passives that have a very small resistance, the instrument suggests to use a LowZ mode. So let's put it into LowZ mode and go back. Now a few things happen. First of all, the voltage level clips at 2 volt RMS. You cannot go above that anymore. But the other thing that changes is that the capacitance value actually changes between these two. So even if I put this to exactly the same setting I had before, I get a different value, and this is closer to the correct value of this capacitor. I couldn't find any information about why that was the difference. Why are these two measurements not the same, unfortunately, in the manual? Perhaps this is something they can clarify to make the user understand better the trade-offs between these two, especially for accuracy of measurement. The other thing that's a little bit unusual is that there is no confidence shown anymore. I think this is probably a bug, and this value is not being displayed. There's no reason why you couldn't have the same confidence measurement here. But you can see that when the source impedance is small, the VM measurement internally and the voltage level applied are much closer together. Now, if you look at the range here, the range has shifted. Now you have these ranges at the top that you can use. So I think there's some clarification is required, especially how the auto ranging and the LowZ mode and regular mode interact with each other, and sometimes it can get confusing. Let's do a quick experiment seeing the benefit of looking at RS and RP simultaneously in this instrument. So I have two capacitors that have the same nominal value. The one is original on the left, and the other one on the right I have modified by adding some parasitic resistances to it, one in parallel to it at 10 kilo ohm and one in series with it at 10 ohm. So of course these are going to have different equivalent models, especially because there's two resistors involved, and depending on the frequency you're going to get totally different values. Let's see how the instrument reacts to this. Now first we can measure the unmodified capacitor. At 1 kilohertz and 1 volt of incident voltage, we're looking at about 490 nanofarad with an RS of 1.46 ohms, which is okay, it's not a terrible capacitor. Now at the same time, we have the equivalent parallel model as well with an RP of 72 kilo ohm. The capacitances are very close to each other. Now this, of course, is an equivalent model at this very specific frequency. Now I can go ahead and change that capacitor and put the one that I've modified. It should behave quite a bit worse than the original one. And let's see, look at that. We're looking at 22.5 ohm now of RS and about 5 kilo ohm for RP. This is a lot worse capacitor. Normally the capacitor like this would be essentially rejected. Now you may ask, well, what if I want to know what the leakage of this capacitor is? That leakage is that parallel resistor that I purposely added to the capacitor. That's going to have to be done at DC. You cannot measure this using this equivalent circuit model at these frequencies. So we do have a resistor measurement capability. I can select that and I can go and choose RDC. Now look at that. What do I get? 10 kilo ohm, which is exactly the resistor I added. So in one instrument, I'm measuring the equivalent models, but I also have an opportunity of measuring the leakage within reason, of course, because we do have a measurement range here that once you go over this, you won't be able to measure it. And just to prove that point, I can go ahead and put the original capacitor back in there that has a very, very high leakage parameter there. Let's go over there and plug this in. And you can see that it cannot find it. It basically goes way over range and tells us that the leakage of this capacitor is going to be very, very small. Let's briefly take a look at the challenge in measuring something in circuit. So here's something I put together. This is just a capacitor in parallel with a germanium diode. That diode has a very small forward bias voltage. Look what happens when I plug this into this LCR meter. Look at the value it gives me. Here we go. Let's see what it says. It says it's about 2 microfarad. That's of course completely wrong. This is a 100 nanofarad capacitor. And it doesn't matter which orientation I plug it in there. I can just flip it the other way. We're going to get essentially the same value. And this is because during the waveform, that diode gets forward biased. And that additional current is confused with respect to the impedance of the capacitor. So the instrument can't tell what is what. And this is exactly where we need to have a small incident voltage. Let's try this on the Rohde Schwarz unit. And let's plug it in. What do we get? Look at that, the CS is 4.3 microfarad, which is also, of course, completely wrong. And the CP is 129 nanofarad, which is much closer. The difference between these two should already tip us off that something is completely wrong. And that's because our incident voltage is 1 volt. Let's change that to a much smaller value, 50 millivolt RMS. And look what happens. We are now much closer between these two values, which makes much more sense, and the value is correct. This is indeed what the value of this capacitor should be. So it all lines up, and this is why it's important to be able to have these very low incident voltages. So let's measure a variable capacitor. Here I have these parallel plate capacitors where you can rotate the plates so that the overlap between them changes, and that changes the capacitance, of course. Right now there is no overlap at all, and the capacitance is fairly small, 11 picofarad. But I want to look at the capacitance as a function of time as I rotate it so I can visualize it. If you click on display mode one more time, you get into this plotting function. And this plotting function allows you to plot all the parameters that the instrument can measure essentially as a function of time. Now, if I have one criticism of this instrument is that the plotting functions are hopelessly underutilized. There is so much potential here to make this plotting more sophisticated. For example, there are no cursors. I cannot zoom into a specific part of the plot, and I cannot change the divisions of these plot variables that are being plotted. They're essentially fixed, and I cannot decouple them. So some of the parameters are going to have vastly different scales, and they're going to be overlapping with each other. I think with just a little bit of change of software, this can become so powerful, and there would be so much more you could do with it with the multi-touch, zooming to different areas, plottings in different places and different axes, and also the font has to certainly become a little bit larger. If they make that change, that would be fantastic. Now, of course, at the time when I'm publishing this review, this change hasn't been made, but once the change is made, I will be sure to make a pinned comment so you can take a look at it and get my impression of it once the changes have been made. So right now I'm plotting two things. One is the capacitance, this is 5 picofarad per division, and the other one is the phase here, which is 50 degree per division. Let's go ahead and rotate this and observe this curve change in real time. Here we go. All right, I'm going to slowly turn it. And as I do that, you can see that the value of the capacitance is going to change. There's some overranging that happens, so there's a little bit of discontinuity in that plot. There we go. We can keep going. And we can go all the way there, and then we can continue rotating it so it goes past the middle and begins to come back down. Those steps that you see is just a sampling rate of the instrument under slow sampling. There you go. Look at that. We got that full curve. That looks pretty good. Now I should be able to stop this so it doesn't continue. Actually, I can't stop this, even though I can stop the measurement here. Yeah, so here the measurement can be paused or continued like so, but apparently in the plot it will continue going. I think that's something they also need to change because we're losing this. It's going to pass by. But you can see the curve going up and down. And that's exactly what you would expect from this. And the maximum and the minimum value are also plotted here, which is nice. So if you go over a wide range of values, you could be able to capture both of those. And next I have a combination of an inductor and a capacitor in parallel. This LC network is going to have some interesting frequency response characteristics. Let's give it a try in the unit. And let's go ahead and plug this in. Here we go. And let's see what we get. So we're measuring at 100 Hertz. At 100 Hertz, the inductor is dominant in that parallel combination. So we're measuring the inductance value 313 microhenry or so, which is correct. Now let's change the frequency to 100 kilohertz instead, 1,000 times larger here. And then press the auto button so that we can find out what kind of component we have. And now we're measuring about 89 nanofarad. So we're more capacitive. And if I go to higher frequencies, for example, at 200 kilohertz, we're going to be even more dominated by the capacitor value, getting closer to the actual capacitor that's in the circuit. It means that somewhere in between these two frequencies, we have the resonance of these two parallel combinations. Now, every good LCR meter is going to have some sweep function, so we can discover that resonance using the internal sweep functions of the instrument. And we can reach that by going into the functions, and we can go down here. We have dynamic impedance measurement. Now once you click on that, you can set the sweep parameter you want. In this case we want frequency, but we can set other parameters as well. We will see that in the next experiment. So we know the frequency range we're interested in, so the minimum 200 Hertz should be okay, and the maximum here is 200 kilohertz. We don't have to go as high as that. We can go to, for example, let's say 130 kilohertz, and we're taking step sizes of 1 kilohertz. So it's going to take a little bit of time to run this, but we will get all those parameters as a function of frequency. Now, one other additional option I wish this sweep had is that it would allow you to specify whether the instrument should auto check the component after every step, essentially pressing this auto button after every step is complete. The advantage there would be that the instrument would at some point switch from inductance to capacitance measurement so that we can get the complete curve, both of those parameters measures. As it stands, it's going to try and measure capacitance, which doesn't, of course, work at some of those frequencies. It's going to have a gibberish equivalent model. However, we're going to be able to discover the resonance by looking at RP or RS, and that's going to tell us everything we need to know. And here the sweep is completed, and you can clearly see that there is a resonance discoverable by looking at the parameter RS. If you look carefully, there's a tiny little red line over here. That's the parameter CS, which doesn't mean much in this particular case, similarly to CP. That's why I wanted the auto function. Now I can't quite decipher what this text at the bottom means. Is that the frequency range? Either way, this definitely can be improved. I can zoom in a bit more, and I can move that a little bit further so we can look at the center and where that is, but there are no cursors. So nevertheless, there's the CSV file that's built into the instrument. Luckily, it's really easy to export that, so we can bring it into a different software like Excel and take a look at it. We can just quickly do this into the file manager over here, and here's the log function. I can select that, and there's the USB already in there. I can just copy it over. That's it. Now I can use the post-processing. And here's the result that the instrument created, a CSV file, and I've gone ahead and plotted everything to make it a little bit easier. The orange line here is the capacitance. Now if you look up until around this frequency, you cannot measure the capacitance, and all of a sudden you get a very large value of capacitance, then drops, and then asymptotically approaches a constant value. And the blue is RS in this case. If I hover over here with the mouse, you can see the frequency is 28.2 kilohertz. And that's exactly the resonance frequency of this LC combination. And at the tail end of the capacitance, we're approaching 92 nanofarad or so. It's getting towards 100 nanofarad, which is the capacitor value. So this is super useful for discovering resonances, not just for an LC circuit like this, but you could look at resonances of components on PCBs if you're designing power supplies or figuring out if the components you have chosen actually would work within the frequency range they intend to. So pretty useful to have this. Now what I have in the test fixture is a PN junction, a diode, and I'm measuring its capacitance directly. I'm measuring it at 1 megahertz with a small active voltage across it so that we don't forward bias it. And the capacitance is about 21-22 picofarad, which is common for a diode of this size. Now we also know, based on semiconductor physics, that if you forward bias or reverse bias a diode, you can change its capacitance. This is the PN junction physical properties. So right now I have the bias voltage set to 0 volt. Let's go ahead and enable that. Of course, enabling it right now makes no difference. We're still measuring the same value. But let's start applying a voltage. I have the diode in the reverse bias condition, so we don't accidentally turn it on. And let's see what happens to the capacitance. We can actually click it up one step at a time. So here's 1 volt of reverse bias. Look at that, the capacitance is now significantly smaller. We can keep going. Let's go to 5 volts, for example. Let's see where we get. And we're at 7 picofarad. So by applying a reverse bias across the diode, we can actually significantly reduce its capacitance as the depletion region grows across the diode. This is completely normal. But we also have a sweep function, so we can plot this as a function of sweep. We can set that up in exactly the same way as before. We can go under functions over here, dynamic impedance, except that we're going to change this now to be the voltage bias parameter. Now we can go all the way to 10 volts. It should be no problem. And step size, we can make the step size a little bit larger. Let's make it 0.25 volts and run this and see what kind of curve we get. And here's the result, and the behavior is exactly what you would expect. The capacitance does continue to get smaller across a negative PN junction bias, and the lowest value it reaches is around 5.5 picofarad or so, which is a factor of 4 reduction from its maximum value. Now, if you look over here, there's a couple of points that's a little bit of an outlier. Let's take a look at this one, for example. So this is at a bias of 4.5 volts, and the reported value is 7.3 picofarad. But if I go back to the instrument at exactly the same bias right now, you can see the value is 7.8 picofarad, which is more correct. I think what's happening is that sometimes during auto ranging and during sweep is grabbing values before they're completely settled down. So I think some delay parameters or making sure that things are stable would be advisable in the sweep function so that these little glitches don't happen. Now let's measure some variable inductor. We have an inductor here connected across our Kelvin clips, and we're measuring it at 1 megahertz. Note how I'm using a stimulus current rather than a voltage to excite the inductor in this case. I can also inject a DC current through the inductor as well, which can saturate magnetic cores, for example, and affect the value of the inductance, and it would be worth studying. In exactly the same way, applying a large DC voltage across a capacitor can affect its capacitance. Right now, I'm not doing anything to this inductor to adjust it, and it's sitting at 1.16 microhenry. Look at the quality factor is about 40, and the equivalent RS 181 milliohms. Now I can insert a magnetic core, a ferrite material, into this inductor, which would then adjust its inductance. I can screw it in here, and we can slowly go further and further into the core of the inductor. Keep an eye out on the value of the inductance. Look what happens. It's slowly going to go up, so I'm going to go all the way such that the magnetic core is in the middle of the inductor. Now let's see what happens now. So we certainly gained some inductance, we tuned the inductor, but notice how we suffered a little bit on the quality factor. And that's because the equivalent RS value got worse as the magnetic core is a bit more lossy, and then will cause the overall quality factor to drop. So we basically increased the inductance at the cost of a bit of the quality factor. But making variable inductors like this is not super convenient because you would have to manually adjust them, but you would find them all over radios for tuning center frequencies, for example. We can also measure transformers using the LCX200. We do have a transformer fixture, which makes the connections a little bit easier as it has labeled where to connect the primary and the secondary of the transformer. And here I have an AC main lines transformer to step down the voltage that comes into your house, for example. So I have connected the primary and the secondary, and then we can configure the instrument for transformer measurement. And we can get a whole bunch of different kinds of measurements for the transformer, including mutual inductance, number of turns, and the phase, and impedance, of course. Now I couldn't find any direct way of plotting the coupling factor, but that's a mathematical function between the mutual inductance and the individual inductors inside. So perhaps it needs to be done in 2 steps. So if you look at this inductor, what do we get for the number of turns? It tells me that we're looking at 6.4. Is that correct? Well, we're going to measure and find out. Now I'm exciting this at 60 Hertz and at 20 milliamp RMS going into it. Then the mutual inductance is 511 millihenries. This is a fairly big magnetic core with strong couplings between them, fairly large inductors. Now what happens if I increase the frequency? Well, let's go all the way to 30 kilohertz, which is well above the frequency where this inductor transformers are intended to operate. What do we get? Look what happens. Your mutual inductance becomes negative, and this is an immediate indication that we are past the resonance frequency of this transformer. It's not going to work very well at this frequency. It's a good quick test to make sure you're operating it in a favorable region. So if you go back to 60 hertz over here, now if we have a 6.44, let's say, number of turns ratio, and we have a 120 something volt coming in, we can calculate what the output voltage should be. It should be around 19 volts or so. But is it the case? We can verify by quickly measuring it. So let's go ahead and use the Rohde Schwarz URE2. So the voltage coming into my house tonight is around 124 volt RMS, and I have the output here directly connected to the input of this unit. Let's plug it into the AC line. Let's wait for this thing to settle down and see what we get. Look at that, 19.49 volt RMS. The turn ratio was about 6.44, and that's exactly what you would expect. It's verified by the measurements of the LCX200. So next I have the surface mount test fixture directly attached, and I would like to perform some binning on some surface mount capacitors that I have. There's one already inside of the fixture, and you can see we're measuring about 1 nanofarad. And these are capacitors that have a 5% tolerance, nominal value is 1 nanofarad. Now one thing I noticed that we don't have in the firmware is any means of averaging, even though we do have measurement speed, slow, medium, and fast, but this is a trade-off between measurement speed and accuracy repeatability. It's not an averaging function, so that definitely should be added to the firmware, and it is pretty important to do averaging, especially during binning. Now to get to the binning function, we just go through this last item here in the menu, and you have to write a small text file, which you can put into the unit, which defines the different binning parameters in terms of percentage or absolute value. It's pretty easy to write, but you cannot define it natively on the screen. You have to load it from a USB, for example. Once you enable that, and then you go back over here, we get the binning menu. I have defined these capacitors in several different bins, 0.1%, 1%, 2.5%, and 5%. Now, if any capacitor I measure is above this value in bin 4, it's basically a reject because it's above the tolerance of the capacitor, and there is a bin here for that as well. Now, once you put it into this mode, you essentially have this triggered menu. You can either trigger externally with software or with some signal from the outside, and you can route the measurements also through the digital I/O in the back of the unit so that you can have some automated measurement. So there's a capacitor in there already, so let's go and press the trigger button. And there you go, it's going to make our first measurement. And you can see that first capacitor falls in the bin of below 2.5%, which is good. It's well within the spec of this capacitor. And here's the result after 25 samples that I went through. You can see the individual samples here at the bottom of the screen. So if you look at this, most of these devices fit under the 2.5% tolerance. Now keep in mind that this is plus and minus, so that if you want to define individual absolute values, I think you also can, but this way anything below and above that fits within 2.5% falls in the same bin. And there were actually no rejects in this case. So this is pretty good. These capacitors are expected to behave very well, but being able to do this binning automatically built into the software can be quite helpful. And let's quickly try out the external bias voltage capability of the LCX here. I have connected the back of the unit to the power supply output here at the bottom. Right now the power supply is disabled and the bias is also disabled. So we do get this little external voltage display here, which is supposed to tell us what voltage would appear on the capacitor or whatever device that you have connected. So it's going to enable the power supply at the bottom. As soon as I do that, I do get the voltage readout over here, even though it's not disabled, which is nice, so you know what voltage is there to be applied to the device. Now this voltage and this voltage are not exactly the same. 9.867, this is 10 volts. Perhaps this is supposed to be within a few percent, but I noticed that this curve is a bit nonlinear, so at lower voltages, for example, if I bring this down to 1 volt, I actually do get a 1 volt reading almost exactly, but as I go to higher voltages, there's a bit of a drift away from it. I think this might be some calibration coefficients that need to be adjusted. So now we can go ahead and enable the bias, and the 10 volts should appear across the capacitor. Let's go enable it. There we go, so it's going to charge the capacitor briefly, and then it gets into this condition where it's hunting for which range to use. And that's why I wanted to have a bit more control over the auto-ranging parameters and the algorithm so that the user doesn't get into a situation where it keeps hunting. We can nail down the auto ranging and force it to stay within one range. We can set, for example, 100 ohms here, and then it settles down. And we haven't seen any change in the value of this capacitor. This capacitor is not affected by it. The 10 volt is too low for it. But I can go ahead and bring this voltage down, for example, to 5 volts. And right now we're reading, and it's going to settle down again. So it says that it should be 4.961 volts. We can measure across and see what it is. 4.941. Yeah, so it's not exactly the same. So these three measurements all differ a little bit from each other, perhaps a calibration. But the most important is to nail down that auto ranging. Now, being able to apply up to 40 volts across any device is very helpful, as capacitors can shift quite drastically with large electric field across the device. And there you have it. I hope you enjoyed this extensive review and experiments of the Rohde Schwarz LCX200. It's a great platform to build on. The firmware does require a little bit of attention here and there, especially in the plotting and auto ranging functions, but given the modern design of it, there is just so much potential that certainly can be leveraged. Now, if I were to design, let's say, an LCX300 version above this one, I would incorporate things like a 2-quadrant source for both current and voltage, whether it's internal or external, and make sure that the auto ranging is a little bit faster, perhaps with overlapping regions and even in solid state if possible, to allow the measurements to be even quicker so that you don't have the relay delay, of course, that comes into it. There's a lot of improvements that can, of course, be made, but in terms of the software, you can do things like resonance detections and being able to find faults in LC circuits or power supplies built in to various personalities. And I think that's probably what they're planning, because this platform with the operating system gives you so much flexibility in future designs, of course. As always, let me know what you think about this in the comment section. I certainly enjoyed working on this. These reviews, of course, take a very long time, so I appreciate your support of the channel as well. See you next time.